On behalf of Vantage, I welcome you back to our series on LED dimming. Today's topic is the dimming performance issue known as dimming linearity. Vantage dimming hardware can be adjusted to compensate for many non-linearity issues exhibited when LED lights are dimmed. To start off, let's define exactly what it is we mean by dimming linearity. This chart represents the ideal linear dimming response. The y-axis represents perceived light output, normalized so that 100% represents the full brightness of the light. The x-axis represents the programmed or intended dimming percentage ranging from 0 to 100%. Our expectation and desire is that the perceived light output would follow this ideal curve throughout the entirety of the dimming range. So at 30% programmed dimming level, I would expect to see 30% light output, and at 60% programmed dim level, I would expect to see 60% light output. Now, without getting into details, for those of you who are familiar with square law dimming or the relationship between spot illumination measurements and perceived brightness, our discussion takes this square law relationship into consideration. At this point, you might be wondering, so why does linearity matter? Honestly, if our lighting control is limited to manually adjusted, unintelligent wall box dimmers, we wouldn't care, because we don't have a marked percentage dim level that we expect to be accurate. We have to adjust to the level we want by using visible feedback of the dim level. But a key purpose of the Vantage system is to avoid the need to constantly change individual dimmers. If we have 8 lighting zones in a room, for example, and we have 4 distinct lighting scenes we want to achieve to provide different looks and set appropriate lighting for different activities, we certainly don't want to be adjusting separately the 8 different dimmers every time we want one of those lighting scenes. One to 45%, another to 70%, and so on. And then for the second lighting scene to 30% and 90%, etc. The power of one button provided by Vantage allows us to dedicate a button to each desired scene so that the user can recall the scenes on demand with a simple button press. A skilled lighting designer distinctively knows what levels he or she wants to achieve, and unless the linearity is good, valuable time may be wasted in adjusting the programmed dim levels to compensate for deviations from ideal linearity. Furthermore, once scenes have been set in a Vantage house, and then later incandescent lamps are replaced by LED lamps, unless linearity compensation is made for the new lights, all scenes would require recalibration. Vantage is the industry leader in compensating for nonlinearity. Let's examine nonlinear behaviors in LED dimming and what can be done with Vantage products to compensate. 3 behaviors that impact linearity are dimming floor, dead travel, and transfer function. In part 2 of this series, we addressed the limitations of LEDs as related to a dimming floor. We showed that a minimum on level or low end trim is applied to eliminate the performance issues often exhibited by LED lights at the bottom of the dimming range, such as pop-on, drop-out, and flicker. We also mentioned that the minimum light output from an LED light source is determined by the current regulation capabilities of the LED driver. This dimming floor is a characteristic of the LED, and there's nothing we can do to extend this floor. So toward the bottom of the range, at some point there will be some deviation from linearity, as we cannot follow the ideal curve below the dimming floor. Dead travel is the term applied to describing the phenomenon where we make adjustments to the program dimming level and there's no change in the dimming level in the LED light source. This can happen when we reach the dimming floor, but for our discussion, dead travel is typically talked about exhibited at the top end of the dimming range. If we start at 100% and then reduce our programmed dimming level, it is not uncommon for us to see that the light output remains somewhat constant for some portion of the range. And then past an E, it will begin to dim at that point. But look how far this takes us away from the ideal dimming curve. Vantage compensates for this by providing a maximum on adjustment, also known as high-end trim. By finding the correct maximum on level, we essentially eliminate the flat response area of the curve above the knee. We essentially take a subset of the full range and we blow it up and we redefine it as the full range. We don't sacrifice anything by so doing, as the light will remain near 100% of the non-dim value. With the reduced maximum on applied, the light begins to respond immediately to the dimming as is necessary for it to be able to follow an ideal dimming curve. Transfer function is a term we use to describe the factors involved in determining the path followed by the light output through the range of dimming. If not ideal, it could follow any path. And often we will see the pathway bowing above the ideal. Sometimes we see the pathway bowing down. Or sometimes we might see an S-curve where it bows up at the beginning and then bows down for the rest of it. And we could see any number of odd transfer functions. The transfer function defines the pathway taken, but we must point out that there are in reality two devices interacting with each other, and each has its own characteristic transfer function. Specifically, there's a transfer function characteristic of the light source and a separate transfer function characteristic of the dimmer itself. So if we were to chart the behavior of three light sources against one dimmer, we might see three different curves. These differences being attributable to the transfer function variations between the three light sources. On the other hand, if we were to chart the behavior of three dimmers against one light source, we might see, again, three different curves, but here the difference is attributable to the transfer function variations between the three dimmers. So our objective is to adjust the transfer function of the dimmer against the fixed transfer function of the light. Vantage is unique in the industry for our ability to modify a dimmer transfer function. There are two separate ways that we accomplish this. The first and the simplest is called the adjust parameter. The analogy we often use to explain the impact of the adjust parameter is that of a rubber band. With the two ends of the rubber band fixed by the minimum on and the maximum on parameters, there's obviously many paths that the rubber band could follow between the 2 points. If the rubber band is bowing up, what we want to do is drive each point down, and we would do that by increasing the adjust factor. If conversely the pathway is bowing downward, we want to drive each point upward, and that is done by decreasing the adjust factor. The second way that the Vantage compensates for transfer functions is to define a customized linearization table, in which we set the program dim levels at 33 points along the curve, and the dimmer extrapolates between these points. This requires considerable more time to produce, but has been found to be very successful in linearizing S-curves and other odd transfer functions. Please keep in mind that the need for a linearization table is rare. This concludes the discussion of dimming linearity and our coverage of LED dimming theory. In our fourth and final video, we will focus on the how-to aspects of applying the tools Vantage provides to you to help you succeed in dimming LEDs.